Another sequence that we want to look at in this chapter is called the geometric sequence. So we talked already about an arithmetic sequence where some value is added each time, and that was the common difference. But in a geometric sequence, we're actually going to be multiplying by the same number, and it has to do with the ratio of successive terms in your sequence. Here you see an example of squares, and so I have, as we read from the left to the right, a series of squares where in each one the number of squares is increasing. So in the first one I have 1 square, then I have 5 squares, then I have 25 squares, 125, 625, and you can see then that in the sequence each one of the squares is being multiplied by a constant term, namely 5 in this case. So that's kind of what we're looking at in a geometric sequence. It's the ratio of successive terms in a sequence that's the same number. Now, down here we have kind of a formal definition of it, and you can see a couple of more examples that we have. This right here is the words, or the numbers I mean, representing the picture we just saw above. So I had 1 square, 5 squares, 25, 125, 625, and the sequence can go on. Now, this common ratio that is going to be the same between my numbers in this particular case is 5 over 1, where we take one number and divide it by the previous number, and each time the ratio will reduce down to be 5. So if we look at the next series, or sequence I mean, we have 4, 8, 16, so forth. If I take 8 divided by 4, that gives me 2. If I take 16 divided by 8, that still gives me 2. 32 divided by 16, it gives me 2. So in other words, the ratio comes from one value in the sequence being divided by the previous value, and it's going to be the same for each one of them. So that's what we call the common ratio. Now, this here is our formal definition of the writing the nth term of our geometric sequence. So the nth term of a geometric sequence is given by a sub n is equal to a sub 1 times that ratio raised to the n minus 1. In other words, this part right here allows me to write a general term in a sequence or anything like that. So let's practice a couple of examples on this geometric sequence. The first example we're going to look at says I want to determine, first of all, whether or not we're looking at a geometric or an arithmetic or neither type of a sequence. So if I want to know if it's geometric, I've got to determine whether or not there is a common ratio between these numbers. So I'm going to take these two numbers here, the first two numbers in my sequence, and I'm going to write them as a fraction. This gives me -2 divided by -1, or in other words, 2. If I did the same thing here, -4 divided by -2, again, would be 2, and these two would also give me a 2. So because there is a common ratio of 2 between these numbers, we can conclude that it is a geometric sequence. I'm trying to spell geometric for you. There we go. Okay, now let's look at the next example. 1, 3, 6, 10. So I'm trying to, again, just determine whether it's geometric. I take the 1 and the 3, or the 3 and the 1, let me say it that way. If I divide that, I get 3 divided by 1, which is just 3. If I take 6 divided by 3, I get 2. And when I take 10 divided by 6, I don't get any of those. I get some reduced fraction, and I know then that it is not geometric. Now just check while we're here. So this right here, because r is not constant, we know it's not geometric. Let's go ahead and check and make sure that it's not arithmetic, or let's determine that. If it was going to be arithmetic, then the difference between these numbers would have to be the same. So 3 minus 1 is 2, 6 minus 3 is 3, and you can clearly see that this is not arithmetic either. Not. So the conclusion for this, if we were trying to determine what type of sequence it is just simply it is neither arithmetic, or geometric. So it can still be a sequence, it's just not either of these two special types.